All right. So if I was me, I would probably do this. All right. So du will be 8dx, and 2du will be 16dx. And u squared will be, and so we have integral, we have 2, we have du, and we have 1 over u squared plus 1 squared, don't we? Okay, now I think I'm going to go over here and I'm going to make myself a triangle. And that's going to be theta. And it's got a plus in it, so I'm thinking tangent. That was the convenient thing there. So, and we got u squared plus 1, so I'm thinking that a is 1, right? So this is going to be pretty nice. So let's use another letter. Let's use v. So v will be just tangent theta, right? So that makes no, let's use u. Sorry. Oops. So that makes u equal to tangent theta. That makes this side u, this side 1, and this side will be the square root of u squared plus 1. Okay? Are we good so far? Okay. So, we have u squared plus 1 will be tangent square plus 1, which is secant square, right? Theta. Secant square theta. And so what we have here is 2 integral 1 over secant square theta. I forgot to put du, didn't I? Sorry. I'm getting ahead of myself here. All right, so we have du equal to secant square, right? I'm sorry. Yeah, secant square theta. D theta. There we go. So we have 2 integral. So du is secant square theta d theta. And u squared plus 1 is secant to the 4th, right? Because it's secant square square. Is everybody good so far? And so this then is going to be 2, 1 over secant square theta d theta. Well, that'd be okay if that was just secant square, but it's not. It's 1 over secant square, right? So what you going to do with that? Same cosine, okay. So we have 2 integral cosine square theta d theta. Now I think we know what to do, right? Because what are you going to do? Yeah, very good. So we use a half angle formula. Good job. So we have 2 integral 1 plus cosine 2 theta over 2 d theta, which gets even nicer, doesn't it? Because Those 2's are going to cancel. So now, we have, I'm going to make 2 integrals out of it. I've got integral d theta plus integral cosine 2 theta d theta. So I've got theta plus 1/2 sine 2 theta plus c. Okay, good. Now, sine 2 theta. I got theta and I got sine 2 theta. Well, u is tangent theta. So theta is inverse tangent of u, right? So we have inverse tangent u plus 1/2. Okay, sine 2 theta. Oh, well, I have theta, not 2 theta. So what you going to do?
Forgive me if I'm wrong, but I think sine of 2 theta is 2 sine theta cosine theta.
Exactly. I need to get it back down to theta. So I'm going to do my double angle formula for sine. So 2 sine theta cosine theta plus c. Okay, so that's inverse tangent u plus the halves, that 1/2 and the 2 are going to cancel. I'm going to go ahead and do my sine theta and my cosine theta. So sine theta is u over u square root u squared plus 1, right? And cosine theta is 1 over square root u squared plus 1. Okay, so this becomes inverse tangent u plus u over u squared plus 1 plus c. Okay, now I have to remember that I made a u substitution from the start, right? So this becomes inverse tangent. Okay, now let's see. What was u? 8x. So inverse tangent 8x plus 8x over 64 x squared plus 1 plus c. And there we go. I think we did it. First, let's think about a definite integral. A definite integral would give us the area under a curve between a couple points, right? Yeah, I'd hope to do better than that. Yeah, that's good. Okay, so I've got a couple of limits here. I've got A and I've got B, and then I have a region that is bounded by the curve, the x-axis, and the limits. And let's say that this function, let's just say it's 1 over x squared. If I wanted to find this integral, to find that area, that wouldn't be bad at all, would it? That area right there would just be the integral from a to b, 1 over x squared dx. And, okay, that would be integral a to b, x to the minus 2 dx. And that's just going to be minus 1 over x evaluated from a to b, right? And we could do that. We could go minus 1 over b minus negative 1 over a. So that'd be actually 1 over a minus 1 over b. I could get a common denominator. That would actually be then b minus a over ab. Okay, so it would be that. That would be actually, that actually makes it kind of easier. That's kind of a formula we could use, right? Now that's a definite integral. B was some stopping point somewhere. But what if there was no stopping point? Now, when I look at this thing, I can see that's a finite area. Okay, what if we didn't stop? What if our graph went on forever and just kept going like that?
Would you not have an infinite area?
Oh, that's the question, isn't it? Would we have an infinite area? So your question was the correct question. Can that area under that infinite region be finite? So this thing is just going to keep going forever and never stop. So X is just going to get infinitely large. Okay, but that presents a problem if I want to figure out what that area is, right? And that problem is that if I do this integral, 1 over x squared, I start at a and then I go to infinity. That makes no sense at all when we talk about finite limits, right? Because that's what's supposed to happen with a definite integral. That's called a definite integral.
Is this still a definite integral technically?
No, it's not. It is now an improper integral. So you don't talk about it in mixed company. So this is an improper integral. The only thing I can imagine we could do now, remember how we talked about, I can theoretically cover the distance in a limit, right? But not practically. So it seems to me like that's what we're going to need to do. Like, what we'll need to do is say, okay, I'm going to say that this will be an integral, and I'm going to leave a space right here because we're going to talk about that. I'm going to say I'm going to go to some value t for this thing right here. Now, that just made it finite, right? That just made it a definite integral if t is of a specific value somewhere. It could be anywhere. It could be anywhere along here. It could be here, 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 here. So we're going to do a limit as t goes to infinity. Now, this is what an improper integral is, and this is what it does. Okay, so then, what do we do? Well, I'm going to integrate it the same way, right? Like, that's just an integral right there. So I would have the limit as t goes to infinity of, I'm going to do the same thing. I'm going to go integral a to t, x to the minus 2 dx, just to do this out, bit by bit like we would if we were doing this. So that's the limit as t goes to infinity of minus 1 over x evaluated from a to t. Okay, so then this becomes the limit as t goes to infinity of minus 1 over t minus 1 over a. And then that becomes the limit as t goes to infinity. Well, just like we had before, right? We had 1 over a minus 1 over whatever that upper limit was, and that was b last time. This time it's t. Does that have value? Okay, now that is interesting. So didn't we just show then that that would have a finite value? That one's pretty similar, isn't it? It's a rational function with a vertical asymptote at the y-axis and a horizontal asymptote at the x-axis. And has a real similar shape. If I go beyond 1, I go 1 over, say, 2 or 1 over 3 or 1 over 4. If I square those, and now I'm at 1 over 4, 1 over 9, 1 over 16. So the graph of 1 over x squared would be squished down farther out that way, right? Out towards infinity. So the question then is, well, does it squish down enough that it makes a difference between that and the function 1 over x? That's a question that we have. So let's see. Let's do the same thing. let's start at some value a, and then let's find this area out to infinity. So we're never stopping here. Okay, so we would do that then by finding this integral from a to infinity of 1 over x dx. But that is an improper integral. So I'm going to say, all right, this will be the limit as t goes to infinity of the integral from a to t of 1 over x dx. And then now this one then would become the limit as t goes to infinity of the natural log of the absolute value of x evaluated from a to t. So that one behaves pretty differently than the last one. So let's see what we have. We have the limit as t goes to infinity of the natural log, and I'm not worried about absolute values if I'm way out there, am I? If I'm on the right of the y-axis, I don't really care. So the limit, the natural log of t minus the natural log of a. Now, the natural log of a, that's going to be some finite value, right? So I'm going to be taking something and subtracting a finite value. But what am I subtracting that finite value from? So is that finite? No, that is definitely infinite. Okay, so that is really interesting right there. 1 over x does not give us a finite result at infinity where 1 over x squared does. That's going to be really important to it. We're going to have some terminology for this, okay? Because this gave us a finite value, we're going to say that this is convergent. So the 1 over x squared function gave us a convergent value. Or in other words, that improper integral in that case was convergent. In this case, because this improper integral gave us an infinite value, we say that it is divergent. And those two terms are going to be real important to us as we get older, like within the next couple weeks. If the integral from a to t of f of x dx exists for every number t greater than or equal to a, then the integral a to infinity of f of x dx is equal to the limit as t goes to infinity, integral a to t f of x dx. Provided this limit exists and is a finite number. Our B. What if it's the other way? What if we're looking at the other side of 1 over x squared? In that case, we would be going off to negative infinity, right? And that would be the bottom limit on our integral. Okay, so if the integral t to b of f of x dx exists for every number t less than or equal to b, then the integral from minus infinity to b of f of x dx is equal to the limit as t goes to minus infinity, integral t to b f of x dx, provided this limit exists and is a finite number. Okay, so the difference is that on the first one, we've got infinity at the top, and our t value is going off to infinity. Limit as t goes to infinity. On the next one, our t's on the bottom because we're in a situation where we're infinite to the left. So our minus infinity is on the bottom, and t is going off to minus infinity. If the limit exists, then the improper integral is convergent. And that's what we found with 1 over x squared. If the limit does not exist, then the improper integral is divergent, which is what we found with 1 over x. Now, here's the thing. What if I have a discontinuity in the middle? Like with 1 over x squared, where we can't put 0 in, right, on either side. Okay? So this is where our part C comes in then. If both the integral from a to infinity of f of x dx and the integral from minus infinity to a of f of x dx are convergent, then we define, and you realize that convergent means that all those conditions exist, right? That the improper integral is convergent, that the limit exists, right? Then we define the integral from minus infinity to infinity of f of x dx equal to the integral minus infinity to a f of x dx plus the integral a to infinity f of x dx. So you see, we can turn it into a sum of integrals that break up at wherever that discontinuity might be. Integral minus infinity to 0 x e to the x dx. Okay, so, well, what I know is that I could write this then, since this is an improper integral, and the bottom limit is negative infinity, I can write this as the limit as t goes to minus infinity, integral t to 0 x e to the x dx. And when I think about how to integrate that thing, what am I thinking?
By parts.
Parts, yeah, because we got two functions that really aren't related at all, right? So let's see. U will be x, and dv will be e to the x dx. Then v is e to the x, and du is just dx. Okay, so one here. So I'm going to have the limit as t goes to minus infinity of integral t to the 0. And I think probably what I'm going to do, and I'll keep it the way I'm going. Okay, so here we go. We've got x, e to the x dx. Okay, good. That's what I was after. So we're in good shape so far. 2 straight across, right? Now, I got to think about what I'm doing here. I'm doing this integral. And this one has limits of integration, right? And it's also an improper integral, so it has a limit on the outside. So when I write this next thing, this x e to the x, well, I'm integrating it. So, I mean, I have to put my limits of integration on it because I'm evaluating it, right? So I'm going to go from t to 0, but I also have to remember that this is a limit as t goes to negative infinity. Okay, good. And then minus, okay, 3. This will be the limit as t goes to minus infinity. Integral t to 0, e to the x dx. Okay, so what do we got here? We got the limit as t goes to minus infinity, x e to the x. We'll evaluate this in a bit. I want to worry about this over here. This will be the limit as t goes to minus infinity. Now, that's just going to be e to the x, right? Evaluated from t to 0. Okay, so now let's do this. Let's do this, evaluating here, and then I'm going to do something. I'm going to do it again in a minute, and show that we can combine it all into one thing. Okay, but for right now, I wanted to be real specific and detailed about the concept that each one of these terms is an evaluation of an improper integral. So we that limit, and then the limits of integration as we go through that first term right there, that we might get lazy and not write that down. That's important. Okay, so here we go. Now, so I'm going to have the limit as t goes to minus infinity. Now I'm evaluating this thing, but the thing is that the first term is going to be 0, right? Because I'm multiplying it by 0. If x is 0, then and e to the 0 is 1, then that's just 0. Minus, okay, now I've got t e to the t. Okay, minus the limit as t goes to minus infinity. Okay, so this is going to be e to the 0 minus e to the t. I'm not quite sure what I should do here as far as this goes, but one thing I could do is I could write this, and the only reason I'm going to do this is because this is a trick that we're going to want to use later in life, okay? T over e to the minus t. That's the same thing, isn't it? Okay, minus the limit. I'm kind of going around the block to get next door, but it's because I want to exhibit this thing that I'm doing right here. Yes, ma'am.
Is it negative t over e?
Yes, sorry. Yeah, I meant to put that minus right there. Now, this is going to be 1 minus, and I could call that 1 over e to the minus t, right? Now, the whole point here is what happens here when I do this? Now, why did I bother doing this over e to the minus t thing? Well, when I put negative infinity in right there where negative t is in that exponent, it just becomes e to the infinity, right? Okay, but I got another problem though, don't I? Because the top becomes infinite. Now, this is why I wrote this thing this way. Because what did I just establish here? I have an indeterminate form. So by writing it that way, I got myself a limit with an indeterminate form that I can use L'Hopital's rule on. Okay, good. So let's see then. So L'Hopital's rule. So I can go the limit as t goes to minus infinity. So that first term there, so that's going to be, well, that's going to be minus 1, right? And the bottom, yeah, negative e to the negative t. Okay, that worked out really nice. And the second one here is, well, that's 1 minus 0, isn't it? That worked out really nice too. So by putting that e to the t on the bottom, we clearly see that we have 1 over infinity. So minus 1 minus 0, so just minus 1. So the whole thing turns out to be negative 1. So now, what is my conclusion here? That it's convergent. That's my conclusion. My conclusion is that this thing is convergent. Integral from minus infinity to infinity, 1 over 1 plus x squared dx. I think we know about that. I think we've been looking at that, but we have a serious problem. I mean, we're infinite on both ends, right? So I'm thinking what we're going to need to do is think about breaking this up somewhere, like that one where we had before, that part C that we looked at a bit ago for improper integrals. Well, what function is that? Yeah, if I find an integral, what's it going to be? Yeah, it'd be inverse tangent, won't it? Okay, so I'm thinking I probably need to break that up at 0. Okay, so let's see. I'm going to say then that this is going to be the integral from minus infinity to 0 of 1 over 1 plus x squared dx plus the integral 0 to infinity 1 over 1 plus x squared dx. And those then are improper integrals, which then I would write as the limit as t goes to minus infinity, integral t to 0, 1 over 1 plus x squared dx, plus limit t goes to infinity, integral 0 to t, 1 over 1 plus x squared dx. Okay, now those I know are inverse tangents. I'm going to start with just the first one. I'm going to do them separately. So I'm just going to have the limit as t goes to minus infinity, integral t to 0, 1 over 1 plus x squared dx. Okay, so this is going to be the limit as t goes to minus infinity, inverse tangent x evaluated from t to 0. Okay, so this is going to be the limit as t goes to minus infinity. Let's see. Inverse tangent 0 minus inverse tangent t. Okay, I kind of need to know something about inverse tangent, don't I?
The arctangent of infinity.
Well, I'm going to worry about 0 first. So I can do this in a couple of ways. I could think about the function of the tangent function between minus pi over 2 and pi over 2. That's what that looks like. And the function value, remember the inverse tangent is the y value, right? What I get back is the angle. Well, when the tangent function has a value of 0, what angle is that gives me that value? Yeah, that's 0, right? That's that dot right there. Okay? So, then that first part there is 0. So really what this becomes then is just the limit as t goes to minus infinity of minus inverse tangent of t. Okay, so let's see. Well, where is the inverse tangent defined? Is it defined everywhere? Where is it defined? Where?
Not 0.
Well, no. It's defined at 0.
Oh.
Where is the inverse tangent defined? Okay, let's go back to this. If I'm going to have an inverse function, the function that the inverse came from, or the inverse function itself, has to be what kind of a function? Yes, it has to be 1-to-1, right? Is the tangent function 1-to-1 from minus infinity to infinity? Say no. No. It just repeats itself over and over, right? So it's definitely not 1-to-1. So what do? We limit it to minus pi over 2 to pi over 2. That's where the inverse tangent function is defined. In other words, it's only defined on the right half of the unit circle, right? Only over here. Okay, so if that's the case, then I'm only looking at, for my inverse tangent, I'm only looking at the possible range of angles, right? From minus pi over 2 to pi over 2. So if t is going to go to minus infinity, and I've got the opposite of this inverse tangent of t, so t is going off to minus infinity. Now let's think about that for a second. So the inverse tangent, t is actually a function value, right? It's a tangent value. What I get back is an angle. Well, if the function itself goes off to negative infinity, what is the angle going to? Negative pi over 2. And then the opposite of that is pi over 2. Good. Is everybody seeing what we're talking about here? Okay, so, well, we got that part. That's convergent. That's pretty cool. That part's cool. So let's look at the rest of it. So now let's look at the limit as t goes off to positive infinity, integral 0 to t 1 over 1 plus x squared dx. Okay, so that's still inverse tangent. So we have limit as t goes to infinity, inverse tangent of t evaluated from 0 to t.
Inverse tangent of x.
So, x, yes, sorry. Right here. So, what do we got? We've got the limit as t goes to infinity. Now, so this will be inverse tangent of t minus inverse tangent of 0. Oh, we already know what that is, right? That's still 0. Okay, so let's see. Now, inverse tangent as t goes off to infinity. Well, that's the same as what we had before. It's just the opposite end, right? So what's that going to be? That's still pi over 2. Yeah, good. So these two things added together then. So then we have pi over 2 plus pi over 2, and that's going to be pi. So this thing is convergent. This is kind of fun, isn't it? Finding these infinite integrals. I mean, who'd have thought that was finite? Okay, the integral from 1 to infinity, 1 over x to the p dx is convergent if p is bigger than 1 and divergent if p is less than or equal to 1. Now, I'm just going to stick that out there right now. You write it down, put it wherever you need to hang on to it, because that is going to be something that's going to be also very, very important to us. But you can look at it and go, you know what? What if p was 1? Well, we already looked at that, right? That's 1 over x. We already know that's divergent, right? Turns out it's divergent if if p is anything less than 1, too. If p is bigger than 1, that's like when we put 2. And we had 1 over x squared, and we found that it was convergent. So that's going to be true for all of them. But if you think about that, we talked about how if you put a square on there, it's like taking the 1 over x values. As we go out to infinity, it's like taking the 1 over x values and squishing them down, right? Because you're going to put bigger numbers on the bottom. So it's going to squish the thing down. Well, if 1 over x squared is convergent, what happens when I cube the numbers in the denominator? It squishes them down even farther, right? And then farther and farther and farther, the bigger p gets. So it seems to me that I could use 1 over x squared to compare to things like 1 over x cubed plus 1. Like maybe I don't know about 1 over x cubed plus 1, but I know about 1 over x squared. I know that 1 over x cubed is squished down farther than 1 over x squared. And if I add 1, I'm only making the denominator bigger, right?
So it's just
So these are concepts that we're headed toward. Okay. If f is continuous on the interval a to b, including a but not including b, and is discontinuous at b. Okay, now that's interesting. It's not even continuous at b. It's discontinuous at b. Then the integral from a to b, and that's weird, even talking about an integral from a to b where we have a discontinuity at one of the limits. The integral from a to b of f of x dx is equal to the limit as t goes to b from the left, a to t, f of x dx. Now let's see if that makes sense. So my limits are from a to b, and t is going to go to b from the left. Yeah, think about a graph. Picture that. I don't know what I've got here. I've got something with maybe an asymptote at b. And then I've got some function that, looks like this. And I'm definitely discontinuous at b if I go on forever, right? And so I've got some left-hand limit a. Then I can say, okay, well, t is going to be, my x value that goes on like this towards the left. So I'm going to approach b from the left. Okay, so that's what that's saying. If this limit exists, and is a finite number. So in other words, that is true as long as this limit exists and is a finite number. Okay? Oh, darn it. Okay, B. If f is continuous on A to B and is discontinuous at A, then this integral, A to B, of f of x dx, and you can kind of imagine what's going to happen, is equal to the limit as t goes to A from the right, integral t to b, f of x dx, if this limit exists and is a finite number. If f has a discontinuity at C, where C is a number between A and B. So not then at the endpoints, but in the middle. And I think, Everett, you asked about that. What if it's in the middle, right? And both the integral A to C of f of x dx and the integral C to B f of x dx are convergent. Now let's think about this for a second. What does that mean that they're convergent? Both of them would have a finite value, right? And if I add up two finite values, what do I get? A finite value. So then the sum of those two things would have to be convergent, right? Then we define the integral as A to B of f of x dx equal to the integral A to C f of x dx plus the integral C to B f of x dx. Just like we said, adding up two finite values. Integral 2 to 5, 1 over square root x minus 2 dx. Now, you see a problem?
2 minus 2 square root 2.
Yep. We have a discontinuity at 2, don't we? Okay. So, here's what I think. I think we're going to do the limit as t goes to 2 from the right, aren't we? That would put us between 2 and 5. If we go to 2 from the right, integral t to 5, 1 over square root x minus 2 dx. Now, so you see how we're applying what we just looked at here. Can we integrate that thing? I think so. How do we integrate that?
Just do a substitution.
Yeah, I think it's pretty simple, isn't it? So we might say, what do you want to let u be?
X minus 2.
Okay, then du would just be dx, right? So I'm going to integrate this separately, and then I'm going to put it back into the limit, okay? I did it the other way before, and I want to just do it this way just because I want to do it both ways so you see it done both ways. But you already know this. So I'm going to integrate 1 over the square root of u du. So I've got the integral of u to the minus 1/2 du. So I have, now let's see, if I add 1 to 1/2, to minus 1/2, I get 1/2, flip it over and multiply, right? So I have 2u to the positive 1/2 plus c, right? But u is x minus 2, so I have 2 square root x minus 2 plus c. But we are evaluating this integral. So what we're going to have then is the limit as t goes to 2 from the right to square root x minus 2 evaluated from t to 5. So we have the limit as t goes to 2 from the right. Now let's see. I'm going to put 5 in for x, so that's going to be the square root of 3. So I'll have 2 square root of 3. And then I'm going to put t in there, so minus 2 square root t minus 2. Now, so as t goes to 2 from the right, so that means I'm getting closer and closer to 2 from above, right? So so it's going to be numbers that are just a little bit bigger than 2, right? And when I subtract 2 from those, what kind of numbers am I going to get?
Small decimals.
Yeah, really, really tiny positive numbers, right? That's the point. I'm getting really, really tiny positive numbers. And how tiny? Well, as tiny as I want them to be. So in other words, 0 in the limit, right? So this whole thing turns out to be 2 times the square root of 3, right? So what did you just determine? That improper integral would be convergent, right? Now I'm stressing this convergence and divergence thing because basically what we're going to be doing when we come back, and we're going to do what's called series. And you know, when I was talking about approaching Henry infinitely, I was talking about a sequence of steps. So a sequence is just a list of things that are sequential. They come in order, right? A series is when I add up the terms of that sequence. And that was when we talked about, well, the sum of the distance there would be 1. The limit of that thing would be 1 as I approach Henry. But, so that's the difference between a sequence and a series. But what we're going to be after is whether or not these sequences and series are convergent or divergent. And that's why we're stressing this whole thing about convergence and divergence. Integral 0 to pi over 2 secant x dx. The integral of secant x dx can be found by doing a little trick here where we would multiply the top and bottom of this thing by secant x plus tangent x. So what we would wind up with then is the integral of secant square x plus secant x tangent x over secant x plus tangent x dx. Now we can let u be equal to secant x plus tangent x. Then du would be secant x tangent x plus secant square x dx. So what we would have then is the integral of 1 over u du, which would be the natural log of the absolute value of u plus c, which would be the natural log of the absolute value of secant x plus tangent x plus c. This will be the limit as t goes to pi over 2 from the left. And this was a natural log, right? Or from the, I think I said right. I meant to say left, didn't I? Okay, so we have evaluated from 0 to t. So we have the limit as t goes to pi over 2 from the left of the natural log of secant t plus tangent t minus the natural log of secant 0 plus tangent 0. Okay, and then we're hoping that that whole secant 0 tangent 0 does something nice, right? And does it? Well, let's see. The secant of 0. Well, we've got our secant graph here. So secant 0 is 1. And then we have our tangent graph here. And the tangent of 0 is 0. Good. So we have, that's going to be the natural log of 1. And the natural log of 1 is 0. So that whole second term there goes away. So all we're working with here then is the limit as t goes to pi over 2 from the left of the natural log of secant t plus tangent t. Okay, so now the question becomes, what about these values at pi over 2? We just looked at them at 0. What about these graphs at pi over 2? As we go to pi over 2 from the left, what does the secant do? It goes off to infinity. And as tangent goes to pi over 2 from the left, where does it go? Yeah, that also goes to infinity, doesn't it? So we wind up with the limit. I'm sorry, we already looked at the limit. So we wind up with the natural log of 2 infinity, which is just the natural log of infinity, right? Which is just the natural log of infinity. I mean, which is just infinity, right? So what would you say about this then? It's divergent, and that's the conclusion we're trying to come to. Is it convergent or divergent?
I got a 50-50 chance of getting it.
Hey, that's another excellent point. I'm glad you said that. So, what does this mean? This means that where we're headed, our sequence and series topics that we're going to cover, it isn't coming up with numbers or coming up with some sort of expression. It's arguments. All of your problems the answers are going to be arguments. So, do you remember when you did proofs in geometry? You're going to start with a problem and you're going to say, is this thing convergent or divergent? And then you're going to go run through an argument that says whether or not it's convergent or divergent. And we'll learn all different kinds of techniques for doing that. Like the comparison theorem. Here comes a technique. Boy, that discussion came at a very opportune moment. The comparison theorem. Okay, you remember how I talked about, like you think about, okay, well 1 over x squared, we know that's convergent, right? And 1 over x cubed is squished down below 1 over x squared. So if I compare those two, and I use 1 over x squared as my thing to compare to, I could say, well, for sure 1 over x cubed has got to be convergent, right? So here we go. Suppose f and g are continuous functions with f of x greater than or equal to g of x greater than or equal to 0 for x greater than or equal to a. So beyond some point a. F is bigger than g. So just like we're talking about, past 1 over x squared is bigger than 1 over x cubed. Okay. A. If the integral from a to infinity of f of x dx is convergent, then the integral from a to infinity of g of x dx is convergent. B, if the integral from a to infinity of g of x dx is divergent, then the integral from a to infinity of f of x dx is also divergent. That makes sense too. If I compare something like 2 over x to 1 over x, well, I know 1 over x is divergent. And 2 over x, those values are even bigger than 1 over x, right? And so if 1 over x is divergent and 2 over x is bigger, then 2 over x has to be convergent too. So let's look at the integral from 0 to infinity of e to the minus x squared dx. Okay, we looked at 1 over x squared, we looked at 1 over x, we know about those. Those are either convergent or divergent. E to the x, well, I'm thinking about that, and I'm thinking, well, e to the x, as x goes to infinity, e to the x goes off to infinity. E to the minus x, e to the minus x, yeah, that'd be like 1 over huge numbers, right? But is it convergent? I don't know. And then when I think about e to the minus x squared, well, those numbers get even bigger, right? And those exponents, and then they become negative. So in the denominator blows up bigger. But so these are the things that you want to imagine as you go into these problems, because one of the things that you want to kind of get used to thinking about is, what do I suspect? Do I have a suspicion? Because if I'm going to compare to something and say they're convergent, I'm going to have to suspect that it's convergent if I'm going to compare it to a convergent one, right? Because if I compare a divergent to a convergent, I really can't conclude anything, can I? It's only if I compare a divergent to a divergent, that's when I can draw a conclusion. So I really need to come up with some kind of an assumption here. Well, let's look at the thing. Let's do a little bit more thinking about this here. What if I was to break this up into bits and go like from 0 to 1, e to the minus x squared dx, plus integral 1 to infinity e to the minus x squared dx. What if I broke this up into pieces? For x greater than or equal to 1, we would have x squared greater than or equal to x, right? That makes sense. And that was kind of what I was alluding to earlier. What is the behavior of that exponent for different values of x? Okay, so on that interval, or on that integral from 1 to infinity, where x is greater than or equal to 1, I know that x squared is going to be bigger than x. That's something that I know. Okay. Now, if that's the case, but those aren't positive, right? Those are negative up in that exponent. So if x squared is bigger than x, then minus x squared would be less than or equal to minus x, right? Therefore, oh my goodness, these are arguments, aren't they? E to the minus x squared would be less than or equal to e to the minus x. Is that true?
Yeah.
Yeah, if I raise e to a smaller exponent, it'd be smaller than if I raise e to a bigger exponent. Okay, that makes sense. Okay, so on the interval from 1 to infinity, e to the minus x dx. Now I'm looking at e to the minus x here, right? E to the minus x dx is equal to the limit as t goes to infinity, integral 1 to t, e to the minus x dx, equal to limit as t goes to infinity, e to the minus 1 minus e to the minus t. Now, e to the minus t, that's 1 over e to the t. And as t goes to infinity, that's 0. So this whole thing is just e to the minus 1. That limit right there. So that integral 1 to infinity e to the minus x dx. Now, why am I caring about this? Well, I've already said I know that e to the minus x squared is less than e to the minus x, right? Okay, so far on this part, from 1 to infinity, I'm finite. Okay? So now, if we were to do this, let's try to follow that theorem, that comparison theorem that we put up here a second ago. And try to make now notice that this is going to be really important here. Notice that, I've got things organized here. I've got an argument that can be followed, and that's going to be super important. You want an argument that can be followed from top to bottom. All the logic is there. There are no gigantic leaps that anybody has to make. Okay. So if I don't want to make leaps here, then I need to state those theorems clearly. So let's let f of x be e to the minus x and g of x be e to the minus x squared. F of x would be greater than or equal to g of x, and g of x would be greater than or equal to 0, right? So they're both positive. And we already decided that for values beyond 1, this would be true. For x greater than or equal to a, which we're going to have be 1. Okay, now since the integral from 1 to infinity e to the minus x dx is convergent, the integral from 1 to infinity e to the minus x squared dx is also convergent. Very good. But have I finished this problem?
About taking care of 0 to 1.
Have I not taken care of 0 to 1 though? Tell me about e to the minus x squared from 0 to 1.
It gets smaller at a faster rate than
Is it infinite? Are my limits infinite? No, they're finite, aren't they? So what about its integral?
No, it's fine.
That means it's going to be a finite value, isn't it?
a finite value plus a finite value.
It's a finite value plus finite
It
value.
means it's converged.
Very good. But we have to state that. We're going to have to state that. A finite number plus a finite number. And this is not going to be sufficient for a complete argument. But a finite number plus a finite number is finite, and therefore convergent. But we're going to come back to this and talk about this next time, okay?